Uh, Mr. Chang, are you here?
Hello.
Hello. I have a question about next week,
Yeah.
or is it next week? Is it this Friday? There's a lecture titled like exam review, right?
Yeah.
What is that going to be about?
Oh,
I'm a
yeah.
bit
So it's
I'm a bit impatient, sorry.
oh yeah. Yeah. So essentially, we are going to so like after this lecture, we finish essentially the first segment of the course, right? So we kind of learn about database, learn about how to use it, learn about how to design application. Next lecture, we are going to essentially go back and do a quick review about everything we have been learning so far. We are going to talk about our expectation in exam, right? To define some scope, right? And we are going to look at some example questions in previous years to go through them together. Yeah, so that's for Friday. Yeah.
Sure,
Does
thank you.
that answer your question?
Yes, it does.
Yeah, cool.
Thank you.
Sure. Okay, so let's get started. So today we are going to finish up a normal form. That's something we left essentially half of the content from last lecture. Okay, so where are we? So we were talking about the process of logical modeling, right? So that's the process that take as input your conceptual model, entity relationship model in this course, and translate that into a relational model. So more concretely, in this course, when we are talking about the entity relationship model, we talk kind of specifically with the entity relationship diagram in our mind. So there are other ways you can do conceptual modeling in practice, but in this course, we focus on entity relationship diagram. And when we talk about the logical model, we talk about relational model, right? So all of my data are stored as a whole bunch of relations. Each relation has a name, has a set of attributes. Each attribute has a name and has a domain, right? So I think we are all familiar with this. And we were talking about the process of doing this translation. And the fundamental challenge is that given one application, right, modeled in your ER diagram, there are so many different ways you can translate them into a logical model. You can merge relations or you can decompose relations. One question that we really want to understand is how can we reason about the pros and cons of different ways of design this kind of logical schema given your application. And that is something we have been talking about over the last couple of weeks, involve the database design theory. Essentially, the fundamental question we want to understand is what is a good database design and how to formally model and enforce the property we want in a good design. So the thing that we have been talking about in the last lecture is something that we call normal form. And that is actually one way for us to reason about the pros and cons of different designs. Essentially, database normalization is the process of structuring a relational database in accordance with a series of so-called normal forms in order to reduce data redundancy and improve data integrity. And last lecture, we talked about so many different normal forms. So first normal form, second normal form, third normal form, right? So for each of the normal form, they are corresponding to one common way to normalize your data. And for each normal form, there are three fundamental questions that we are curious about. First, if you give me a database relation schema and a set of functional dependencies, FD, how to decide whether the schema together with those functional dependencies satisfy a given normal form. So to understand this question, essentially we kind of need to define all the property we want inside the normal form and understand how to check it, how to check whether a given schema and set of functional dependencies satisfy a given normal form or not. And the second question is, if you give me the schema and the set of functional dependencies in your application that satisfy a given normal form, what are the set of properties that we can say about this design? For example, in some of the normal forms, like we talked about BCNF in the last lecture, as long as your relational design is in BCNF, we can say there will be no data redundancy caused by functional dependency. So for each of the normal form, we want to have a whole bunch of properties that we can say about any relational design that satisfies the normal form. And the third question we want to understand is, given relational schema and given a set of functional dependencies, assuming R and FD does not satisfy a given normal form, how can we create a new schema, R prime, such that it satisfies the normal form we wanted to satisfy? Last time we talked about, if your schema is not in BCNF, you can do decomposition, right, to generate a new schema that's in BCNF. If your schema is not in third normal form, you can run the synthesizer algorithm to generate a new schema to turn your design into something that's in third normal form. Essentially, for each normal form, this is the three fundamental questions that we want to understand. So in this course, right, so we will actually talk about five different normal forms. In the last lecture, we already talked about 4 of those. First normal form, second, third, and BCNF. The common thing among all these 4 is they all curious about or worry about all those data redundancies caused by functional dependency. And today we are going to talk about a different normal form, that is the fourth normal form. Different from all the 4 normal forms we talked about in the last lecture. Today, the first normal form, we actually cares about data redundancy, not caused by functional dependency, but caused by something called multi-value dependency. And the relationship between these 5 different normal forms is also pretty clear. So starting from the first normal form all the way to fourth normal form, they are much, much stronger in the sense that there are going to be fewer amount of schemas in each of those, right? So like all the schema in first normal form will also satisfy first normal form, right? So there's a hierarchical structure between all of these 5. So before we talk about the first normal form and the multi-value dependency, let's just refresh our memory about the first and 4 normal forms we talked about last time. The first normal form is very simple, right? So it only have essentially one requirement, that is all the value you have in your database need to be atomic. What do we mean by that? We mean every single value, you can think about every single cell in the table, okay, need to be a value that cannot be further decomposed. A counterexample of that is you cannot have a set list, right? Like all of those type of like kind of collection of values in the cell. So this is one example. The first relation is in first normal form because every single value is atomic. For the second example, you can see this cell contains a set, right? So it's a set of tuples, it's a set of values, and the second design is not in first normal form, okay? So in practical database system, you could do both, right? It's your decision about which one makes more sense for your application, right? But when we have a relational design in first normal form, sometimes it makes it easier for you to reason about functional dependency, right? The second normal form that we talk about is second normal form, right? So essentially, when you have a relational schema R and a set of functional dependencies FD, we say this design is in second normal form if and only if every non-key attribute, every attribute that's not part of the key, is minimally dependent on every key. So what do we mean by minimally dependent, right? It means that we do not have an attribute, non-key attribute, depends on only part of the key. So to make that more concrete, let's look at this example, right? So you have your student attends lecture, you have the ID of the student, you have which lecture student is taking, you have the name of the student, you have which semester students in. If a student took 4 lectures, right, you are going to see 4 tuples here, right? 28106, this is one student. This student took 4 courses, right? So you can see there's a functional dependency from the ID to the name and semester, right? Given the student ID, I know the name, right? However, the ID itself is not the key of this relation because I also have the lecture information here, right? The key is actually the combination of the first 2 columns, the ID of the student and the ID of the lecture. So in this case, if you look at name and semester, these 2 non-key attributes partially depends on the key. That is, they depends on part of the key, right? So if that happens, this schema will actually not be in second normal form. And as you can see, because of this partial dependency on the key, this relation is going to have data redundancy, right? So, and that is why for every single student here, right? So we need to store multiple copy of the name, simply because this evil functional dependency from a from the ID to the name and semester. And then we can make this even stronger because even if a design is in second normal form, it doesn't mean it doesn't have any data redundancy caused by functional dependency. So a stronger notion is something we call the third normal form. We say relational design R is in third normal form if and only if for all functional dependency that you have from alpha to B, where alpha is a set of attributes and B is a single attribute, at least one of the following conditions hold. Either this functional dependency is trivial in the sense that the left-hand side is a superset of the right-hand side, and that's a functional dependency that's always going to hold, right? So, or B is an attribute of at least a key, okay? Or the third condition is the left-hand side, alpha, is a super key of R, okay? So here, super key means a superset of some candidate key. So let's look at this example, right? So you have 4 attributes, A, B, C, and D, right? You have 2 functional dependencies. One is from AB to CD, another is from C to D. Right? If you look at this, if you look at the second functional dependency, right? So we can actually check whether it satisfies one of these conditions. In this case, it's not trivial, right? Because the left-hand side is not a superset of the right-hand side. And also the right-hand side is not an attribute of a key because the key of this relation is AB from the first functional dependency, right? So D is not part of the key. And also C is not a super key, right? So the key of this relation is AB, C is not a superset of that. And because of this C to D functional dependency, this relation is not in third normal form, okay? So the intuition behind the third normal form is if you have an evil functional dependency alpha to B that does not satisfy any of these conditions, often it is the case that the alpha, the left-hand side, is actually one entity that deserves its own relation, okay? So one example is third normal form try to get rid of those like a transitive dependency, right? You have something from A to B or something from B to C, right? So in this case, I really want to decompose it into essentially 2 different relations. So I think we have a question. Yeah, just go ahead.
The question was, when do we consider a functional dependency to be evil? And we got answered in the chat with whenever it doesn't satisfy any of the 3 listed conditions.
Oh, yes. Oh, yeah, yeah. So like we say a functional dependency is evil is because of that functional dependency, this design is not in this normal form, right? And in the context of third normal form is if you have one relation, if you have one functional dependency does not satisfy any of this, it is evil for third normal form, right? Does that answer the question?
I'm pretty sure it does. Thanks.
Thank you. Okay. And then we talk about another normal form that's even stronger than third normal form. Why do we want this? Because even if you have design in third normal form, it still could have data redundancy caused by functional dependency. And we want to have something even stronger, right? To get rid of even more redundancy. So, and that is something called BCNF. So we say a relational design R is in BCNF if and only if for all functional dependencies from alpha to B, at least one of the two conditions hold. Essentially, we get rid of one condition in third normal form. Either this functional dependency is trivial, or the left-hand side is a super key of R. Okay. So if you think about these two conditions, both of them are actually pretty trivial in the sense that, like, for almost, it doesn't really allow any non-trivial functional dependencies in that relation. So intuitively, right? So that actually forces you to only store the same information once in each relation. So let's look at one example, right? So here you have one relation, right, with three functional dependencies: ABC to D, AD to BC, D to C, right? So essentially, there are two candidate key of this relation. From the first functional dependency, you get, okay, one candidate key is ABC. From the second functional dependency, you get, oh, another candidate key is AD. This design is actually in third normal form, but not in BCNF, right? So the reason is, if you look at the third functional dependency, it is not trivial, right? And left-hand side is not super key, right? But the right-hand side is part of a key, right? So the key of one candidate key is ABC, the right-hand side is part of the key, right? So this is okay for third normal form, right? So this design is actually in third normal form. However, it's not okay for BCNF, so it's actually not in BCNF. So, and as you can see, there could be a data redundancy like in this relation, right? So, I mean, that is why you could have data, and the reason behind it is you could have data redundancy even if you design in third normal form, but if you have those BCNF, you actually will not have data redundancy caused by functional dependency. It still could have redundancy, okay, but not caused by functional dependency. So given these two notions, right, BCNF and the third normal form, we also talk about essentially three questions, right? So one is, how can you turn a database schema into BCNF? And second, how can you turn a database schema into third normal form? And then is, why do we even need these two notions, right? So what is the trade-off between third normal form and the BCNF? So when we talk about decomposition algorithm, right? So for BCNF, right? So your input is relational schema R, your output is kind of R1 to Rn, right? You want to make sure two conditions hold. First one, R1 to Rn is a lossless decomposition of R, meaning that if you join them together, you will perfectly recover all the information in R. And second, you want all of this, R1 to Rn, are in BCNF. So that is the property we want. So later on, we are going to see this algorithm is very important because you can have that for BCNF. And later on, when we talk about the fourth normal form, it's a very similar algorithm, right? So it's kind of makes sense for us to refresh our memory to talk about it. So it's very simple. You start from your original relation, R, and then you check whether there exists some relation in the result side that is not in BCNF. If that relation exists, it means that there must be one evil functional dependency that makes that happen, right? Because of alpha to because of alpha to beta, Ri is not in BCNF, and that thing must exist, right? If you cannot find it, then all the Ri will be in BCNF, right? By definition. So you find that evil functional dependency, and you decompose Ri into two relations. One of them contains all the attributes in alpha and beta, and second contains all the attributes except those in beta. Okay. So, and then you replace Ri with these two smaller relations in your result set. You continue to do this until all the relations in your result set is in BCNF, then you return. So let's look at this example, right? So on the right-hand side, you have 3 functional dependencies. And then you start from asking, okay, is this relation is in BCNF? Clearly it's not, right? And the evil functional dependency, as we talk about, is the one from D to C. Because of this relation is not in BCNF. So we take this and decompose this relation into 2 smaller relations. One contains both the left-hand side and the right-hand side of this functional dependency, give you a relation with 2 attributes C and D. Another contains all the attributes except those in right-hand side that give you A, B, D. So as you can see, this one give you a lossless decomposition of the original relation. If you join them together, you get your original relation. And then you go through each of them and to see whether they are in BCNF. If they are in BCNF already, you are done. Otherwise, you keep decomposing them. So this is just one illustration about what happened, right? So if you have alpha to B in your original relation, you decompose it. You put alpha and B together into one relation, and you put the other part into another relation. We also talk about how to deal with third normal form, right? So here, we want to have an algorithm that takes as input R, decompose it into R1 to Rn, such that it is lossless decomposition, and also every single relation is in third normal form. So we talk about the synthesizer algorithm, right? So it's different from BCNF that have a decomposition algorithm that goes in a top-down fashion. You start from a large one, you keep decompose. For third normal form, the algorithm actually goes bottom up, right? So you will compute the basis of all the functional dependencies. For each functional dependency in the basis, you create one relation. And then if none of this relation contains a key, you add a relation with a key, and then you merge them. If there's a one relation contains attribute set alpha, another relation contains attribute set alpha prime, and if alpha is a subset of alpha prime, you merge these two. Okay, so this is the process for third normal form. So let's look at one example, right? So here on the right-hand side, right? So we first compute the basis, which give you 2 functional dependencies, right? One from A, B to C, another from C to D, right? And then you create one relation for each of this. And you also check whether this contains the key, right? So here in this case, my key is AB, right? So I have one relation contains AB, so I'm fine, right? And then you try to merge them to see whether you can merge. Here I cannot merge because ABC is not a superset or subset of CD, right? So then I'm done, right? So this is kind of one example of the synthesizer algorithm. Yeah, so I think we have one question. Go ahead.
Yeah, I'm not sure if I understand, like, what does it mean add a relation with a key? So we add, for example, what I could imagine an ID field, but what else is in the relation?
Oh yeah, so for example, right? So so for example, after you create one relation for each functional dependency, right? You could have, I mean, it is possible that none of those relations contains a key for your original relation, right? And in this case, you will create a new relation that only contains the attributes of a key, right? For example, if your key is AB, you will have a new relation with only A and B there. Okay, that makes sense?
Oh, so we basically choose a bunch of attributes and then put them into a relation on their own.
Yeah, exactly. Such that those set of attributes form a key.
Okay, thanks.
So I always want to have one relation have the key. Otherwise, I cannot join them back. Right? So yeah. Okay, great. So this is a synthesizer algorithm, right? So we also went through one example about this, right? So given the schema, you can do the third normal form decomposition, you can do the BCNF, right? So if you put them side by side, right? So the trade-off is actually very clear. When you are doing the third normal form, right? So it's actually going still to have data redundancies caused by functional dependency. If you do BCNF, you are going to get rid of all those redundancies caused by functional dependency. So it's actually, in some sense, BCNF is actually more efficient. However, when you are doing BCNF, it is possible that you are going to lose some of the functional dependencies during the process of decomposition. And when you are doing third normal form, you are going to preserve all the functional dependencies, right? So in some sense, the trade-off between third normal form and BCNF is a trade-off between correctness, whether you preserve all functional dependencies, and efficiency, that is whether you get rid of all the redundancies. So this is just a quick refresh of memory about what we were talking about last time. Today, let's talk about the data redundancy that's caused not by functional dependency, but caused by another type of dependencies. And that type of dependency is something we call multi-value dependency. And here is actually one example for that. So here you have one relation with 3 attributes, A, B, and C. And as you can see, condition on the value of A, so assuming that you know A must pick value A, condition on this, the choice of value of B and C are independent, in the sense that if A corresponds to B and BB, that is 2 values, for each possible value you can choose for C, I always have B and BB, right? If you, like if the value A corresponding to 2 B values and 2 C values, you are going to have 2 times 2 equals to 4 number of tuples in the final relation. If you have a relation look like this, we say there's a multi-value dependency from A to B, and also there's a multi-value dependency from A to C. Now we can make this even more formal, right? Formally, we say there's a multi-value dependency from alpha to beta for a relational schema with 3 set of attributes, alpha, beta, gamma, if and only if for all T1, T2 in R in one relation instance, if T1, T2 matches on alpha, it means that you must be able to find 2 tuples in R, T3 and T4, such that all these 4 tuples, T1, T2, T3, T4, they match on the value of A, on alpha. T3 takes the beta value of T1, T4 takes the beta value of T2. On the other hand, T3 takes the gamma value of T2, and T4 takes the gamma value of T1. So this is a very kind of complex condition, right? It might look very confusing, but what it's trying to say is actually very, very simple. It actually says that if I have a multi-value dependency from alpha to beta, what does it even mean? It means that if you give me 2 tuples, T1 and T2, they match on alpha, but they have different values on beta and gamma, I must be able to find T3 and T4, which is just a swipe of the value on beta and gamma. I have a T1, so I have T3, take T1's beta and take T2 and take T2's gamma, and I have T4, take T2's beta and take T1's, sorry. So and I have T4, take T2's beta and T1's gamma. Okay, so I mean, if you look at the color coding, it's very, very clear, right? I have T1 and T2, I must be able to find the T3 and T4 that essentially swipe the value of beta and gamma. If I can do that for every single pair of T1 and T2 that matches on on alpha, then I say there's a multi-value dependency from alpha to beta. And similarly because definition is symmetric, right? Whenever you have multi-value dependency from alpha to beta, you will always have multi-value dependency from alpha to gamma, right? So I think someone raised hand. Go ahead.
Yeah, so just to be clear on the formula on the left there, T1, T2, T3, and T4, they must all be different tuples, right?
Doesn't need to be.
Well, but if they can all be the same, then doesn't that mean that there's a multi-value dependency between any 2 sets of attributes?
No, because it's for all, right? So at the beginning you have for all.
Yes,
for,
but
for any pair.
Of course.
Right. So they could be the same, they could be different, right? But because of for all, you need to consider all the pairs, right?
Sure, thanks.
Yeah. Cool. Okay, so this is a multi-value dependency. And let's look at one example, right? So assuming we have a relation contains 3 attributes, the person ID, the language the person speaks, and the program language that person knows how to use, right? So in this application, right, so there's a conditional independence between language and program language. So if you look at this, essentially you have the MVD from the person ID to language, you have MVD from person number to programming language. Okay, so and very easy to see when you have MVD, right? It can also result in anomalies and redundancies, right? So it's not caused by functional dependency, but caused by multi-value dependency. Multi-value dependency might look a little bit counterintuitive, but the very intuitive way to think about it is to think about it in terms of joins. So essentially, when you have alpha, beta, and gamma, there's 3 sets of attributes in relation R. When you have MVD from alpha to beta, it means you can actually decompose R losslessly into 2 relations. One take alpha and beta, another take alpha and gamma. And then if you join them together, you get your original relation. If you can do that, it means there's actually a multi-value dependency from alpha to beta and also from alpha to gamma, because you can see the whole thing kind of symmetric. So in fact, decomposition R into R1 and R2, right, in above is lossless, right? So like if like one of this is true, right? So, okay. So last week, when we talked about the functional dependency, right? So we talk about different ways to reason about functional dependency. That is, if you give me a set of functional dependencies, how can we derive new functional dependencies, right? So because we can do that, we can actually run our decomposition or synthesis algorithm for BCNF and third normal form, right? When we do third normal form, we do compute the basis, right? Which require you to do some inference on the set of functional dependency you have in your application. So we need to do this similarly for multi-value dependency. We want to understand the relationship between different multi-value dependencies. So similar to functional dependency, we have trivial multi-value dependencies. Assuming you have a relation R with 2 sets of attributes, alpha and theta. So there's always going to be multi-value dependency from alpha to alpha theta, right? That is, if you give me kind of a subset of attributes in R, right? So there's always going to be a multi-value dependency from that subset to the whole R, okay? So the proof of this is actually pretty simple. If you want to prove there is MVD from alpha to alpha theta, what do we need to prove? What we need to prove is the following. We need to go back to definition, right? If you go back to definition, right? So beta, right, is actually the whole relation R, and the gamma, the other side, right? So it's empty, like in this case. So essentially the thing you want to prove is for all pairs, T1, T2 in R, if these 2 tuples matrix on the value of alpha, you want to prove there exist T3 and T4 such that they all match on alpha, and T3 and T1 matches on alpha theta, T4 and T2 matches on alpha theta. Because in this example, if you go back to the definition, the gamma is actually empty side, right? So third thing is actually going to be trivially true, right? So how can you find this, right? For any pair of T1 and T2, you just set T3 equal to T1 and T4 equal to T2, then you are done, right? So this is actually like for any pair of T1 and T2, I can always find T3 and T4, right? They could be the same as T1 and T2, right? We say nothing in our definition of multi-value dependency. They could be the same, right? So by setting them the same, T3 equal to T1, T4 equal to T2, you constructively find T3 and T4 for T1 and T2 that satisfy this condition, and then we are done, okay? So this is one very trivial functional multi-value dependency. When we say MVD is trivial, we mean this. We mean the right-hand side is actually the superset of the left-hand side. So similarly, you can prove something like this. Assuming you have a relation with alpha and theta here, there's always going to be MVD from alpha to theta, okay? So if you have alpha, right, so there's always MVD from one subset of attributes to the rest of the relation, okay? So we also have other kind of like trivial MVDs, right? So assuming you have 2 sets of attributes, right? So you have beta and you have alpha, beta is a subset, right? So there's always MVD from essentially from alpha to beta, right? To prove this, it's actually pretty simple. So what do you want to do? You want to prove there's MVD from alpha to beta. What do you need to do? You need to prove that for all pairs of T1, T2, if they match on alpha, you can always find T3, T4 such that all the 4 tuples match on alpha, T3, T1 match on beta, T4, T2 match on beta, T3, T2 match on gamma, T4, T1 match on gamma. So it's very easy to check. You just set T3 equal to T2, T4 equal to T1, you are done. Okay, so this is another trivial MVDs in relations. And this can become more interesting. So if you have a functional dependency, not MVD, very clear functional dependency from alpha to beta, it implies that you are going to have a multi-value dependency from alpha to beta. So we call this rule promotion, right? So you can actually promote a functional dependency to MVD. Whenever you have FD, you have MVD, okay? So how can you prove that? The proof is simple, right? You always go back to definition. If you want to prove alpha, MVD from alpha to beta, you need to prove this, right? So I think now everyone just really clear about what this is, right? You need to find, like for all pair of T1, T2, you need to find that T3 and T4. Because there is functional dependency from alpha to beta, and because we know that T1 and T2, they match on alpha, we know they also match on beta, right? Given the definition of functional dependency. And because of that, you can set T3 equal to T2 and T4 equal to T1, then we are done, because all those tuples will have exactly the same value on beta because of the functional dependency, right? And then by just setting T3 and T2, T equal to T2 and T4 equal to T1, you kind of construct T3 and T4 that satisfy the MVD condition. Okay, and then all the other conditions just hold trivially. So this is just another example about how to prove laws related to MVD, right? In general, you go back to definition, right? And you try to reason about it. So in this case, right, whenever you have functional dependency, you have multi-value dependency. However, the other way around is not true, okay? Whenever you have multi-value dependency, it doesn't mean you have functional dependency. So let's think about the one counterexample, right? So actually this relation give you that counterexample. In this case, you have MVD from person ID to language. You have, but however, you do not have functional dependency from person ID to language. Why? Because you can see 3002, there are multiple values in the language side corresponding to that person, right? So in this case, there's no functional dependency, but there is a multi-value dependency. Right? So you can promote, like whenever you have FD, you have whenever you have functional dependency, you have multi-value dependency, but the other way around is not true. Okay. And laws of MVD can get more interesting. So let's think about this case, right? So whenever I have an MVD from alpha to beta, I will also have MVD from alpha to essentially to the rest of attributes that's not in alpha and beta. Okay. So the proof is actually trivial, right? Because if you look at the definition of MVD, you can see it's actually symmetric, right? So it's very, this one is very easy to write down. Okay, the proof. So similar in this one, right? So when you have whenever you have person number to language to MVD, right? You can imply you will also have the MVD from personal number to the rest of the attributes, which is programming. Okay, so these two always come side by side. Another inference rule is called multi-value augmentation that look a little bit like this. Whenever I have MVD from alpha to beta, and if I know delta and gamma, the two subsets of attributes, and delta is a subset of gamma, then I have the MVD from alpha gamma to beta delta. So this is something that we call multi-value augmentation. And then let's try to prove this together. Okay, so let me switch to my iPad and then we can actually draw it together. And you can see how to prove MVD, that is like how to reason about MVD. That's actually, yeah, like reason about some non-trivial inference rules for MVD. Okay. So what do we want to prove here, right? So here, essentially what we want to prove is if you have MVD from alpha to beta, and if you have delta is a subset of gamma, you want to say, there's actually MVD from alpha gamma to beta delta. So how can we prove this? Okay. So here we are going to give you kind of a very simple illustration about the way to think about it. We are not going to write down the formal proof. Right? So you think in this way: you have relation R, and then you have attribute like alpha, you have attribute beta, right? And then you have your attribute gamma, and sum of it is delta, right? And then of course you have the rest of the attributes that call it theta. So what do we need to prove for this? What we need to prove for this is if assuming there's T1 and T2 in this relation with the same value on alpha, right? Of course, they have different value on beta, and okay, B1, B2, right? So they have different value on, yeah, let's in this way. Let's call it alpha, beta 1, beta 2, okay? They have theta 1, theta 2, and then they have different value on gamma, right? So like they share the same value on the left hand side, right? Instead, they have the same value on alpha. Also, they have the same value on gamma. If I have these two tuples, what I want is to find a tuple with the same value on alpha and gamma, but swipe the value on essentially like on beta, delta, and the rest of tuples. Okay, so I first have T3 take the same beta and delta value as T1, right? So I have 1, and because delta is a subset of gamma, right? So they will always the same, right? So and then T4 take the same beta value, right? And then they actually swipe. I want T3 take the theta value of T2. I have theta 2, I have theta 1. Okay, so this is what I want. I want to say as long as you have T1, T2 look like this, I can always find T3, T4 look like this. So how can we make that happen, right? So this is actually very simple. Okay? So because I have alpha to beta in my like on left hand side, right? So that means that if you give me T1, T2, I can always apply this rule. I can always find T3 prime and T4 prime with the following. They have the same value as T1, T2, right? But they actually swipe the value of beta and the rest of attributes, right? For example, T3 prime will take beta 1, beta 2, and then they swipe, okay? Then T3 prime will take gamma and theta 2, and T4 prime will take gamma and theta 1, right? So, and as you can see, this is because of the multi-value dependency from alpha to beta, right? And then these two actually matches, right? So you just set T3 equals to T3 prime and T4 equals to T4 prime, then you are done. Okay. So that's just a kind of very simple way for you to prove this. Yeah. So of course, like when you go back home, you can try to write down the formal proof, right? But the intuition is actually already there. Okay. And there's one more rule here, right? So there's something called multi-value transitivity, right? Which is essentially when you have MVD from alpha to beta, and you have MVD from beta to gamma, right? So then you have MVD from alpha to gamma, right? So the proof is actually very simple, right? So actually write down a proof sketch here, right? If you are interested, you can actually try to go through it. And the game is the same. You give me T1, T2. I want to find T3, T4. And then you give me a construction to like for T3 and T4. Okay. So one question that we kind of want to understand is we talk about all those inference rules for functional dependency, right? Does all of them apply to MVD, right? So it's actually not. And that is why when you try to reason about MVD, you really need to make a distinction between that and functional dependency. Okay, not all the inference rule that sounds so natural for functional dependency also apply for MVD. So let me give you one example for that. So when we are dealing with functional dependency, right? So we used to have this rule. It's called decomposition rule for functional dependency. Whenever I have alpha to beta gamma, it implies I will have alpha to beta and alpha to gamma. Clearly, this is not true for multi-value dependency, right? So here's just one example, right? So in this relation, I have a trivial MVD from language to kind of personnel number and programming. I'm just a trivial MVD, right? So, but given that I do not have MVD from language to personnel number for clear reason, right? So this is just one counterexample that you cannot apply the same type of inference rules as functional dependency just to multi-value dependency. Whenever you are reasoning about multi-value dependency, you probably need to start from scratch, right? By just thinking about all those inference rules that you know are true for multi-value dependency. And we talk about a lot of them, right? So in the previous slides. Okay, so this is the first half of the lecture, right? So let's take a break, and in 15 minutes, we'll continue. Okay, so let's continue. Yeah, we talk about multi-value dependencies and how to reason about it. So now we are ready to define a new normal form called force normal form. So we say a relational design R is in force normal form if and only if for all the MVD that you have in your application, at least one of these conditions hold. Either this is trivial, okay, or alpha is the super key of R. Okay, so as you can see, it's actually very similar to BCNF, but we just kind of replace functional dependency with multi-value dependency. So the first thing that we can say about force normal form is that it is stronger than BCNF, strictly stronger. That is, if you have a relation design in force normal form, you can say it is also in BCNF. So how to prove that, right? So to prove that is actually very simple. You just prove the other way, right? So you want to prove that if R is not in BCNF, it implies it is not in force normal form. On the left-hand side of this, that R is not in BCNF actually implies that there must be at least one evil non-trivial functional dependency alpha to beta in R, right? Otherwise, it will be in BCNF, right? So, and then because we know the promotion rule, right? Whenever there is functional dependency from alpha to beta, there will be MVD from alpha to beta. It means that there will be a non-trivial multi-value dependency too, right? And then that implies this R is actually not in force normal form, and then you're done, right? So this is just a very simple proof about the statement that if R is in force normal form, it implies it's also in BCNF. So now let's revisit all the questions that we have been talking about for other normal forms, right? So first one is if you give me a schema that's not in force normal form, how can we decompose it? How can we decompose it into a set of smaller relations, R1 to Rn, such that first one, they form a lossless decomposition of R, and second, each of these Ri is also in force normal form. So algorithm of doing that is actually very simple. It's actually very similar to the one you have in BCNF. You start from the result side that only contains just single relation. And then you keep checking whether all the relations in the result side are in the force normal form or not. If that's not true, it means that there must exist some relation Ri that's not in force normal form, which means that you must be able to find one evil multi-value dependency for Ri. And then you take that, you decompose Ri into two relations. One contains both alpha and beta, and second contains everything other than beta. And then you just replace Ri with these two small decomposition, and you keep doing this until all the relation in the result side are in force normal form, then you are done. Okay? So this is very similar to what you have in BCNF, but here we try to reason about the multi-value dependency instead of functional dependency. So let's go back to this, let's look at one example, right? So here, assuming you have a professor table, right, with personnel number, the name, area, right, advisor, whatever, right, language, programming language, right? So once you have this, you can actually go back and try to check how to decompose it into BCNF or into force normal form. So as you can see, right? So whenever you are doing that for force normal form, you end up having essentially smaller like relations. For example, when you decompose it into BCNF, you will end at having a relation with personnel number, language, and programming language. And then you do nothing on this relation. Why? Because there's only multi-value dependency, but there's no other functional dependency anymore, right? So there's no functional dependency from personnel number to language. There's no functional dependency from personnel number to programming language. Essentially, if you are doing BCNF, whenever you have these two relations, you are done, right? However, as you can see, even though it doesn't have any data redundancy caused by functional dependency, you still have data redundancy caused by multi-value dependency. When you are trying to decompose it into false normal form, you are going to further decompose this relation into two smaller relations, right? And then you are going to have essentially 3 relations in the output instead of 2. So as you can see, right, so there's a fewer amount of data redundancy in false normal form. Essentially, there's actually no data redundancy caused by functional dependency and the multivariate dependency if your schema design is in false normal form. Of course, there could be other source of data redundancy, but they are not caused by multivariate dependency if your relational design is already in false normal form. So as a, like in summary, right? So we talk about 5 normal forms, all the way from first normal form to fourth normal form, right? And one of them is always stronger than the other, right? You have the hierarchical structure, and there are much more, right? If you go to Wikipedia, there's actually a whole bunch of other normal forms, right? And all of them have different type of properties, have different pros and cons, right? Different guarantee on the correctness, that is preservation of the dependency, and also on the efficiency, right? How much redundancy they can actually get rid of, right? When you are building a real world application, right? When you are really trying to think about, in which normal form I should normalize my database to, right? You probably need to go through some of this and try to do the exercise to really think about the pros and cons of those, right? What is the efficiency, right? Are they going to lose the functional dependency I really cares about, right? Maybe you don't care about that piece of functional dependency, then you're fine, right? If you really care about the correctness, right? You kind of, and there's only that many functional dependencies you can use. So whenever we are talking about normal form, right? So we are talking about the process of translating a conceptual model into a logical model. So remember a couple of weeks ago, actually before Easter, right? We talked about the process of, if you give me a ER diagram, right? So we give you one algorithm to translate that into a relational model, right? Just to refresh our memory, right? Every single entity set in my ER diagram become a relation. Every single relationship in the ER diagram become a relation, right? And then we merge relation with the same key. So if you do this, right, this will actually automatically give you a relational design that at least insert normal form. If you think about why, it is because all of the functional dependency in the ER diagram are caused by kinetic constraints from relationships, right? If you follow this step by step, right? So like turn entity set into relation, turn relationship into relation, merge relation with the same key, right? So it's very easy to see that you will always have a relational design that's insert normal form. So another thing that we want to discuss is we talk about all those normal forms. One is stronger than the other, right? So the hierarchical structure is higher always the better, right? So given one application, should I always turn that into the first normal form, or maybe the 6th or whatever normal form that even stronger than the first normal form? I mean, is that something that higher the better? It's actually not always, and there is actually a very interesting trade-off. So recently, right, so you might see, and this course we talk about data normalization, but in practice, sometimes you also hear people talk about database denormalization, right? Which is actually try to put things together instead of put things separately, right? So the benefit of that is actually it could be faster for you to fetch information, right? So look at, so like look at this example, right? So you have a very huge table. You have personnel number, you have name, you have city, street, zip code, whatever, right? It's so ugly, right? So I mean, there's so many different functional dependencies, there's so many redundancy in this relation, but it doesn't mean it's a bad one, okay? In some applications, you might find it's beneficial to put all the information together to lower the level of normal forms, right? Because when you put everything together, you actually have better locality. If your application, whenever read your data, always need this decomposition, always need this combination of informations, putting them together will make the reading process much, much faster because I do not need to join multiple tables for this. On the other hand, right? So what's the downside? It's easier to read, but it's very hard to maintain the consistency. Whenever you want to change something, you need to touch multiple tuples because they are all denormalized, right? So they, I mean, you do not have a higher level of normal forms right? You have so many data redundancies, you kind of need to update a lot of tuples to make the data consistent. It's easier to read because of locality, but it's very hard to maintain. On the other hand, right, if you do normalization to a higher normal form, you can decompose this very large relation into a whole bunch of smaller ones. And they altogether form a lossless decomposition of the large one. So the benefit of doing this, right? So is that it's very easy to maintain, right? I do not have data redundancy caused by those dependencies. Whenever you want to update or insert tuples, I only need to touch one tuple per relation and then I'm done, right? So, but on the other hand, it could be very hard to read simply because whenever I need, for example, the zip code together with a personnel number, together with content and city, I need to join multiple relations together. And that is often very slow. And as you can see, for normal form, it's not always the higher the better, right? What is best for your application is something you need to think really carefully, specific for your application. Okay, it's not, you cannot say like whatever application I have, I always do the highest normal form, right? So you are going to end up with something that's very, very slow. So again, in practice, right, you need to pick essentially the normal form that actually makes sense for you. Okay, so far, right? So like in the first lecture, we talked about structure of the course, right? So essentially we have two segments. In the first segment, we want to teach you how to be a good database user, right? You have some application you want to build, how to model it using a relational database, how to reason about different designs, and how to implement it using a whole bunch of SQL queries, right? So, and in the second segment, right, so we are going to teach you about essentially how database work under Instacava. Whenever you have a SQL query issued into a database system, what is the work database is trying to do to answer that, right? So today is the last lecture for the first segment, okay? So far, we finished everything we want to teach you in this course about how to be a database user, okay? So in the next lecture, we are going to have essentially a review session, right? We are not going to talk about anything new in the next lecture. We are going to go through from the beginning about everything that we have been learning so far to make sure everyone is on the same page, right? And also when you are learning the whole thing in a sequential way, when you get back, some of the previous concept will actually make more sense. And we are going to do that together on Friday. And then we are going to talk about essentially the scope and assumptions we are going to make in the exam, right? For example, whenever we talk about relational model, it's always a set semantic, not a back semantic, right? Whole bunch of kind of precise scope for the exam. And we are going to go through some of the example questions we had in previous years, right? To help you to understand our expectation. So that's what we are going to do on Friday. And then next week, we are going to spend one lecture to talk about something that's not going to be in the exam. That is, how can we do those advanced analytical workload inside database? How can you do machine learning there? How can you do data mining, right? To make sure when you finish this course, not only you know how to do SQL queries, but you also know in modern database systems, there are so many other functionalities that goes beyond relational query that you can do inside the database, which could come handy when you building the real thing, okay? So, and then next Friday, we are going to switch gear. We are going to talk about database systems. We are going to open the black box up and we are talking about, whenever we have a query, here is the structure of a modern, not modern, of a traditional relational database systems. And here's all the steps that database is doing to bring the information from the hard drive to you as a user. So today we are finished a little bit earlier, right? So if you have any questions, I'll be here to answer them. Otherwise, I'll see you guys on Friday. Yeah, thank you.
Mr. Zhang, there's a question in the chat, I think, like third last column on slide 19, something.
Oh yeah. So I just replied it. So I
Oh,
will
you
think
did?
about
Okay,
it,
so
and
never mind.
so I think it's a typo on the slides, but I need to think about it carefully. And if it is, I will update the slides. Yeah. Yeah, go ahead. I think there's questions. Yeah, just go ahead. Hello.
Yeah, I have several questions, but
Yeah.
I have to looking for the correct slides. I don't have it in front of me. Just a moment, please.
Sure.
Thank you. All right. Professor, would you please let me share my screen?
Sure. Yeah, go ahead.
Thank you. Okay. Can you see the slides now?
This is a functional dependency, right? Yeah, I can see that.
Mm-hmm. Last time in the last lecture, you told me that in this distinct case,
Yeah.
just this case with several entries in the database, it is a lossless decomposition. Is it correct?
Yeah, let me
It's
go
on
through
the
this.
right side.
I think so, right? I mean, at least for this specific instance, right? So when we talk about lossless
Okay,
decomposition, often we talk about for all the possible instances, it should be lossless, right? But for this relational instance, if you join it together, you will get the original relation, right?
Correct. All right. But then you told me that in general case, we have to think of the bigger pictures, like how it would be advanced, it would be modified after that. It could be, it could lead to an not lossless decomposition. Is it correct?
Yes, I remember so. Yeah, I think so.
Yeah. Okay. Then let me go back to this slide.
Yeah.
And this is the same case. This is almost the same case because the child just with solely the name, we cannot ensure so sure that in the future, without any addition conditions, be sure that
Okay.
else is the only child and will be the only child with this name. Is it correct?
Okay. So let me make my statement a little bit more precise, and we can reason about it. Okay. So if you go back to 43, right?
Excuse me?
Yeah.
Sorry?
So if you go back to slide 43, yeah. So essentially, if you look at this decomposition, right? So it is lossless for this relation instance.
Yep.
Right. So in a sense that if you if I give you this zip code relation with 3 tuples, you decompose in this way, you join it back, you are going to be fine. So when we talk about lossless decomposition, right? We essentially means that for any possible instance of zip codes, whether this decomposition is always lossless, and that is not, right?
Yes,
yeah.
but with the same.
So that's what I mean, right? So and then you go back to
argument.
Yeah, and then if you go back to 42, right? So in this case, right, because I have the functional dependency from child to mother and child to father, it doesn't matter what parents relation you gave me. Whatever you gave me, I can always decompose it into the 2 smaller relations, and when I join the back, I will always get the original relation back. That is what what we mean by this decomposition is lossless, right?
But if I insert one more entry to the father and mother child tables with following information like child name is Els, father name is Johann 1 or Johann 2, and then I'm not going to have the lossless decomposition anymore because it just correct in this distinct case. Is it?
Yeah. So like when you change your smaller like relations, right? Of course, your joint result will change, right? but lossless decomposition has nothing to do with the updates of the small relation. So it is essentially like for any relation instance you give me as a parents relation, I can always do this decomposition and join them back. I get the same thing, right? So when you update it, if you really want to think about it as update, you will have a new parents relation, and then every single small relation will change. You join them back, but then you get a changed like large relation at the end.
Okay,
So-
then in general case, this is not lossless. Also in this example, if I'm not mistaken.
No, why? So okay. So what? So why do you think this is not lossless?
Because we stated that here, what we see here is not a lossless decomposition. It's just correct in this case, but in general case, this is not. Am I mistaken something?
Okay, so yeah, so I'm trying to think about the fundamental question you are asking. So
I
not
think-
yeah, so not all the decomposition are lossless, right? So we are on the same page about that, right? So
why? My question was, why is it here? We can say definitely that is not lossless. I agree that it's
okay,
not
okay,
lossless.
okay.
But
I see.
here we say it's lossless. No, there is case that it's
Okay,
not lossless as well, right?
Okay, now I understand. Okay, sorry. Yeah. Okay. So I will make sure I add one slide in the next lecture for the review. I give you a precise condition about something being lossless.
Yep.
Yeah. So that's a very good question. So I get the problem of how I talk about it. Yeah. So I will make sure in the next lecture this problem is fixed. Yeah.
Yep.
So essentially you are asking, given a schema R, given a functional dependency, right? So how can I decide whether decomposition losses or not, right? So like we have one condition, like I think in slide 40, something like that.
Slide 40.
Yeah, so like essentially, if a decomposition is lossless, it actually means that like you have the function dependency that look like this, right? But I will like expand it and give some more example for this part next time when we do the review.
Thank you very much.
Okay. Yeah. Sorry for the confusion. Yeah.
No problem. And I have another question. If no one, I'm not sure if anyone's still here and have
Yeah.
a
So let me
question,
keep
but I have
notes on that.
some.
Okay. Yeah. So I will make sure next time I walk through one example. Yeah.
Okay, can I go ahead and
Sure. If there's no other questions. Sure. Yeah.
slide? Can you see this PowerPoint file lecture 12 or do?
No, I can only see I can only see 11 right now. Yeah.
Okay, I'm gonna stop it and do it again. Nice.
Yep.
Here in normal form, I'm not sure today we saw that you have an underline for A and B, but in the 12th normal form lecture, we don't have it.
Okay, yeah, so like here you have A, B, C, D, right? So if you look at the first function dependency, A, B, C to D, right? Then it means A, B, C is the key. It's one kind of the key.
Okay, then I would like to know whenever you write a statement like this, the functional dependency like this on the left-hand side, they are always the key. Is it correct?
Oh, no. Okay, so what is a key, right? So key need to satisfy two conditions. First one, that subset of attributes need to decide all the other attributes. For example, here you have ABC, decide D, right? So ABC together decide everything else. That's one condition, right?
Yeah.
And second,
I understood about the key as well, but how can I say? we don't have any definition at all in this case. And secondly, we just have two data in our table. For instance, it's just correct in this case, and in general case, it could not be true.
What do you
Or am I
mean? So
mistaken?
like in general case, ABC is always the key because I have that functional dependency, right?
Mm. And okay, then in this case, D is also a key, or is it not?
No,
It's
no, no,
not a
no,
key, right?
no. Here, D is not the key, right? So, like, what is the key? So key is okay. So assuming I have A, B, C, D, right? Assuming I have functional dependency A, B to C, D, then A, B is a key because when I know the value of A, B, I know the value of C, D, right?
What if I have this? If I modify the table and give more detail to the table, I add more entry.
Oh yeah,
Then finally, I'm gonna have it.
but this going to violate your first functional dependency.
Oh, okay, that's right. That's right. That's
Right.
right. Okay.
Yeah. So it could be confusion, but essentially, whenever you say alpha is a key, it means that you have the functional dependency from alpha to all the attributes.
Okay, I get it.
Right.
Yeah.
So
Yeah,
here
it's
D
clear.
to C is not because D doesn't. There's no FD from D to A, D to. I mean, essentially, if you want to make the statement that D is a key, you need to have D to A, D to B, D to C, D to D. Right. So in this case, it's not true because you only have D to C, right?
Okay.
And
I get it.
yeah, cool, perfect.
Yeah, super. These were my questions. Thank you.
Okay, great. Yeah, so like
Thank you
in the
very
next lecture, I will make sure your question about lossy decomposition get answered. Okay. Yeah, thank you for that question.
Yeah. Thank you.
Cool.
And have a nice day.
You too. Okay, so if there's no other questions, I'll see you guys on Friday.